All righty. Good evening, everybody. Ooh. How's everybody doing? Good. Excellent. Good. That was an amazing musical performance. Again, just give them a round of applause at the end for that. They're still back there. Thank you. Yeah. Welcome to the third lecture in our spring series here. I unfortunately missed the last one, but I know it was really good because I know Rebecca Bernstein always gives a great talk on the GMT. This season, we actually have been featuring a lot more of our more senior scientists. You heard from Rebecca just spake, and next time you hear from Tony Pirro. Usually we feature more of our postdocs, and so our only postdoc this year is tonight's speaker, David, so I'm excited you get to hear from him. Before we get started, I want to do our usual thank the Huntington for hosting us, thank the Norris Foundation for helping fund this series, and thank all of our volunteers at Carnegie and the Huntington for helping get you in the room and make all that happen. So tonight's speaker, David, he's a theoretical astrophysicist. This means he doesn't use the telescopes. He might use them a little bit, I don't remember. But for the most part, he does his work on computers. And this is super important work because for people like myself who take observations, his work allows us to interpret it. And he works particularly on supernova, a very exciting field. These are exploding stars. And you're going to hear all about that tonight. Probably has some really cool movies, I assume. We'll see. And so David did his PhD work at Princeton, so not too shabby there. Went to Lawrence Berkeley Lab for his first postdoc, and then came to Carnegie as a Hubble Einstein Fellow. Once again, not too shabby. And so we're super excited to have him. I also point out that he's a local. He grew up here in Southern California, and I think his family's here. Some of them are here somewhere. So I know they're probably very excited to hear from him. So with that, let's welcome David out. David, come on out.
Thank you, John, for the warm introduction. And thank you, individually and collectively, for the courtesy of your attention. I'm David Vartanyan, and today I will take you on an odyssey as we explore the explosive, vibrant depths of massive stars, stars tens of times heavier than our sun, which for a few brief moments in their dying throes can outshine entire galaxies. Throughout my soliloquy today, I will share with you computer models, simulations I've developed with my group that show how these core collapse supernovae explode. And what I show here is one such model that's a star 17 times the mass of our own sun, 17 solar masses. If you were to place this star in our own solar system, where the sun is, it would extend in size all the way to Earth's orbit 5 times over. This means that every planet out to Jupiter, including Jupiter, would be engulfed inside this supergiant star. What I show here is only the inner Earth-sized core. This is a few thousand kilometers in a wingspan of such a massive star. This is where the action begins. This is where the core collapse supernovae begin, and the star explodes in a few seconds. Now, my talk emphasizes the last 60 years of supernovae study. Carl Sagan famously said that if you want to make an apple pie from scratch, you must first invent the universe. It's probably true. That probably holds true for supernovae as well. So our journey will begin just a few years prior to the last half century, where we find ourselves at our first sojourn 5,000 years ago in Burzahum, India, in the year 3000 BC, where I showed this artifact here. This is a petroglyph, an etching in stone that shows 2 hunters, one with a bow, one with a spear, hunting this majestic horned elk. And in the background sky, you see 2 bright doodles. One is likely our sun, and the other could be the first recorded detection of a supernova. In fact, supernova, abbreviated SN, HB9, would have been visible 5,000 years ago from the Indian subcontinent. This is speculative. It's not verified. I'm by no means an archaeologist. Some days I'm hardly an astrophysicist. But the first verified records in the archives and the annals of history dates back just 1,000 years to SN 1054. That's the year of detection, and it corresponds to what's known as the Crab Nebula, this beautiful geometric structured explosion. And we have enduring archives dating back to this year, to the year of detection in the Song Dynasty of ancient China. Now let's go forward a few more years. We find ourselves in the 1960s, where some of the first detections of supernovae were amongst, with other telescopes, through the Burakhan Observatory situated in the beautiful peaks of Mount Ararat, Armenia. In the 1940s, as the German front advanced into the USSR, into the Soviet Union, a particular 2.6-meter lens was scuttled from the war front and brought to Armenia, where it would then form the optics for one of the telescopes seen here. Over the next 2 decades, it would go on to detect dozens of supernovae and hundreds of galaxies, including new discoveries, under the auspices of Dr. Victor Humboldt-Simeon. Now I want you to look at the beautiful 2 peaks here in Mount Ararat. This is named after King Ara the Beautiful, who's equal parts man, myth, hero, history, and legend. And he was so handsome that Queen Shemirami of neighboring Assyria demanded his hand in marriage, and he declined. And so she invaded Armenia to force his hand, in a matter of speaking, in marriage. Courtship has changed clearly over the millennia. Now, as fate would have it, there's Queen Shemirami. King Ara was struck in battle, and he died tragically. I want you to note the incline of his body, the repose of his back, and the bend in his knees. As story has it, the imprint of his body molded the 2 peaks of Mount Ararat. Now, moving from star-crossed lovers back to exploding stars, we find ourselves on a fascinating night in the year 1987, 39 years ago. And this is the background of our own Milky Way. It's called the Tarantula Nebula, when immediately we saw a star explode. Supernova, abbreviated SN, 1987A, the first of 3 detections that year. This is one of the most recent, most explosive supernovae we've had the courtesy to see in our own backyard, cosmically speaking. Such an event is rare. We expect only a few per century to occur within our own galaxy. We're overdue for one. But at the same time, California is also overdue for an earthquake, so hedge your bets accordingly. Now, as instruments have developed and improved, you heard Dr. Bernstein speak 2 weeks ago about the Giant Magellan Telescope and the James Webb Space Telescope. We've seen a growing number of supernova detections. One of the favorites is Cassiopeia A. This is a false color image, but this again occurred within our Milky Way. It likely went off in the 17th century, though the records there are fuzzy. And we have been able to follow it more or less for around 4 centuries. With the launch of James Webb just 2 years ago, this space telescope with the famous honeycomb pattern of mirrors, we have been able as a community to take unprecedentedly high-resolution images of supernovae like Cassiopeia A. And I want to point out that there's a green tidal wave here whose origins are unresolved. It has been affectionately termed the green monster. That is a scientific name. And if you look, we see in these high-resolution images a whole suite, a whole series of structures. You see these plumes, you see filaments and voids and bubbles and even tidal waves. There's a whole vernacular dedicated to describing the morphology of these exquisite explosions. And off to the side, I want to point out label number 6 here. This is an actual magnified on the top, an actual light echo, a reflection of the light from the explosion off the dust around it. And so we can not only observe the structure inside and around the exploding star, but in its vicinity, in its neighborhood. Now, not all supernovae are bright. This is supernova 2023 IXF, detected around 8 megaparsecs away in what's known as the Pinwheel Galaxy. This was first seen by amateur astronomers as part of this collective unistellar community science effort. Some supernovae are much more vibrant, closer, brighter, This is supernova 2014J, looping over. That little star right there is able to explode and shape and outshine its entire host environment. These explosions, if they're close enough, will be visible for days, weeks, months, even during the daytime. And they're especially fundamental to understand. Supernovae directly produce exotic objects which you may be familiar with, like neutron stars and black holes. For context, a neutron star is the equivalent of taking something as heavy as our sun and squeezing it into the size of Pasadena. On the drive from here to Carnegie Observatories and back, I will have gone around a neutron star. It's so dense that 1 teaspoon of a neutron star weighs more than all of Mount Everest. You may also be familiar with the black holes, which are the collapses under gravitational forces of objects so massive with fields so strong that not even light can escape their gravitational tug. And that's why they're called black holes. Now, if you were to be brave and dive headfirst into a black hole, you would feel the atoms in your head down to your toes strung out in a process known as spaghettification. And that is also a scientific term. We're able to model these directly from our computer simulations. On the left, I show you a black hole in the very center with a disk of matter around it and a jet powering outward. On the right, you can see this almost insignificant blob. That is a neutron star formed in our models from a core collapse supernova explosion. Now, even more profoundly, these explosions provide us laboratories to study exotic, extreme environments, high temperatures, high densities that we cannot reproduce or sustain here on Earth. And supernovae also provide the cosmic cornucopia of chemicals which comprise the human existence. That means the calcium in your bones, down to the carbon in your beers, and the oxygen and the iron in your blood cells being pumped extra hard as you try to keep up with my fast talking, were all forged in the hot, dense furnaces of these explosions. Carl Sagan famously said that we are made of star stuff. It would have certainly been less prosaic had he said we are made of radioactive waste. One such explosion, like, again, our favorite Cassiopeia A, produces tens of thousands of Earth masses of each of these elements, and you can see them in our observations. This is silicon, sulfur, calcium. I want you to note and keep in mind the interesting 3 structures I've circled here, these 3 lobes of iron produced in the explosion. If our models are at all accurate, we must be able to reproduce these structures. And so 3/4 of the atoms in our body are formed directly or indirectly through these massive stellar explosions we call core collapse supernovae. And so it merits to understand how these stars actually explode. Allow me to introduce to you this idea of an onion shell. Stars like our own sun, which is small, it's average, not particularly exotic, burn through nuclear fusion hydrogen in their cores into helium. And this is what powers the light from our sun. As stars get progressively heavier, they get hotter and they burn heavier elements, helium, carbon, oxygen, silicon, eventually up to iron. And so much like an onion has different shells, different layers, so too does a star, which has iron in the interior of its core and lighter elements out to hydrogen in its mantle and then its envelope. Now, massive stars follow the James Dean mantra of live fast and die young. Whereas our own sun is expected to live for around 10 billion years, a star that's 20 times the mass of our sun will live a comparably short life of 1 million years, a pittance. And at the end of its short lifetime, its innermost, zooming in right here, iron core becomes too heavy to support itself against the force of gravity. And so gravity pulls the core inward, and it collapses in on itself in less than a second. Now, much like if you take a spring and squeeze it, let go, it'll bounce back out, so too do the innermost cores of these massive stars overshoot, overcompress, and they rebound out. And as the core bounces like a spring outward, it drives a shock wave. And just like a shock wave can sweep you away at the ocean, so too do the shocks inside these stars sweep away the matter around the core. And the shock grows and expands and it propagates outward, growing until eventually it stalls. And the reason is, we're looking at the innermost core of a massive star. This shock, from when the core collapses and bounces outward, tries to bury its way out, but it's buried underneath the heavy mantle of a massive star. So how do you blow up a star? We're going to go back in time a few more decades to the 1930s, where a seemingly unrelated problem in physics would have profound consequences for our supernova study. In the 1930s, scientists, including Enrico Fermi and Wolfgang Pauli, were studying a reaction that many of you may remember from your own high school chemistry textbooks just a couple years ago, where you smash an electron into a proton and deform a neutron. That's it. And in fact, this reaction is how you form neutron stars from supernovae. But before you get to that, Fermi, Pauli, other scientists saw that in this reaction, there's a tiny bit of energy missing. Whenever physicists come across a problem that they cannot solve, they invoke a new particle. And they knew just 2 years ago in 1930, the neutron had been theorized and detected. They knew the missing particle here had to be neutral, like a neutron, but much, much tinier. And so the name neutrino was born, initially tongue-in-cheek, but the name stuck. And we find out that this could solve this missing energy. Now, going back to our problem earlier, neutrinos are not just one species. They're different particles that all change shape and interact, and so in many ways, they're really multiple particles in one trench coat. Now, recall the stalled shock. We knew, going back to the future by a few decades, by the 1950s, we knew that the cores of massive stars collapse, and they liberate much of the energy stored in gravity into neutrinos. Think 99.999% released as neutrinos. So if we can harness just a few percent of this ambient neutrino energy and put it into the star, into the stalled shock, we can revive a failed explosion into a successful supernova. Problem solved? No. The problem is neutrinos have a notoriously small area of interaction. They interact very weakly. To give you a number, the neutrino's area is around 10 to the negative 40 square centimeters. Now, to put that in context, every second, each one of you is being bombarded, inundated by 100 billion neutrinos from our sun, zipping in, day out, every second over every square centimeter of your body. That means every fingernail-sized portion of your body is being bombarded by neutrinos. By the time I finish the sentence, another trillion have gone through. Yet over the course of a lifetime, let's say 100 years, although as physicists are not particularly known for our healthy lifestyles, over the course of 100 years, you can expect, on average, to not even experience a neutrino interacting, giving energy, scattering, being absorbed by the atoms in your body. That means if you look around your rows, taking the middle rows because those are longer, you can expect that maybe 2 or 3 people in each row have ever felt the grazing touch of a neutrino. As part of my PhD program in Princeton, I put together an astrophysics through dance performance. And you see here yours truly as the stalled shock being bombarded by these very talented neutrinos. So now, is the problem solved? No. So let's put this all together and put it into one of our computer models, or let's run a simulation. I take here a star that's not very heavy, only 13 times the mass of our sun, and let it run. This is the core bouncing, and it drives a shock wave that expands outward. And these bubbles you see, this boiling and bubbling, is due to neutrinos. We can't see them, but we can see their effects. And the shock grows, and it expands, and eventually it will explode. The shock's actually increasing. It's decreasing in size, but it's bouncing around. It'll explode eventually, I hope. It's bouncing a bit more vigorously right now. It's head banging around. but it's not exploding. Did I put the neutrinos in here? Why won't it explode? It was the question faced by dozens of supernova scientists for more than half a century. We thought we knew how stars explode. We've seen them, for better or for worse, but we cannot explain them with our models. Why? I'll leave you on that cliffhanger and fulfill a promise I made at the beginning of my talk to give you a brief timeline of supernova developments over the last 60 to 90 years. In 1934, Walter Bode, on the right here, and Fritz Zwicky on the left, Bode was actually a scientist at the Carnegie Observatories then, identified this new observation that they'd seen, which they coined a supernova. It was a very bright burst of light. It comes from the Latin novus, meaning new, or bright, an explosion, a rebirth. 1 year later, Subramanian Chandrasekhar identified the mechanism of these exploding stars, triggered by the collapse of their massive, dense cores. So while Bode and Zwicky coined supernova to explain what we observe, Chandrasekhar coined the core collapse to explain the engine, the theory behind it. And you put it together and you get a core collapse supernova. This is then codified by George Gamow and Mario Schoenberg in the 1940s, who concluded that the collapse of a massive star's core is responsible for a supernova explosion. And they also identified that neutrinos, these exotic particles, were emitted when a star explodes. They did not identify these as the cause of explosion, merely an association. Then there was a pause for the next 2 decades during World War II and the post-war era, where many of these scientists were involved in the Manhattan Project. Then in 1957, Margaret Burbidge on the left, with her husband Jeffrey, and William Fowler and Fred Hoyle put together what we now know as the current theory of stellar nucleosynthesis. In other words, supernovae produce the atoms in our planets, in our sun, in Earth, and in us. Then a decade later, Sterling Colgate and Richard White put together the first computer model of our supernova. And this is where our troubles began, 60 years ago. On the left, right here, is not Clint Eastwood, that's Sterling Colgate. Then 2 decades later, Hans Bethe and Robert Wilson would put this story all together, that neutrinos produced in the collapse of a massive star somehow produced an explosion. 2 years later, we saw 1987A. Again, that was detected first by the Magellan telescopes in Chile, operated by Carnegie Institute. And for the last 40 years, we have struggled to explain how these stars explode. 60 if you go back to Colgate's first models. Now I want to situate you with the following. A supernova is little more than a gravity bomb. The core collapses, and it converts its energy stored in gravity into the energy of an explosion. Much like on a roller coaster or a swing, where you see this dance between gravity and velocity, so too in a supernova. Now, while in a roller coaster, you're harnessed in, and that transfer is mediated by the belt buckle and the harness, and you holding on for dear life. In the supernova, neutrinos are taking you for the ride. And so we then go ahead and model the explosion, and I include this here to show you the equations we solve in our computer models. And there are 2 points to take away from this. First, the beautiful results that I will share with you, the movies, the images, are all built on this bedrock of theoretical buttress. I'm not pulling them out of the air. Second, these equations may look foreign to you, but they contain concepts you are all very familiar with. These are just saying that energy, mass, momentum are conserved. And so the second reason I showed this slide is to communicate to you how astrophysics can simultaneously be both so alien and so familiar. Now we take a star and we divide it up into a bunch of cells on our computer model, and in each of these little grids you see here, we evolve those equations and we see how neutrinos and matter interact to find out if the star actually explodes. So let's try that again. Remember that the first model, 13 times the mass of our sun, failed to explode at around a half a second. This is now 25 times the mass of our sun. And again, the colors here, you can think of as a proxy for temperature. Hotter colors, hotter temperatures. Let's let it go. the core bounces, you see the shock form. These infalling bullets are where the elements like nickel will later form. This bubbling is due to neutrinos, and it begins to grow just like the other data. We pause it now. Right when the other model failed, we pause this one, take a snapshot, and let it continue. And now we see the shock expands, it grows in size, and the star looks like it's actually exploding. Look at the structure. It looks so visceral, so organic. And this model indeed explodes. So we're left with more questions and answers. Before, why does it not explode? Now, why does it explode? Two sides of the same coin. And so, just to emphasize again, we have failed collectively as a community. We've built on the prior years, the prior decades of progress, but until the last 10 years, models would not explode. And so over the next few minutes, we're going to take an effort to MacGyver and make our own star explode. First, we'll need a bulb of onion and a garden hose. Put those to the side. Here I show you one of our first model results, where we take a bunch of stars that are shown here from 12 to 25 times the mass of our sun, each a different color, and we see if they explode or not. On the y-axis here, I show you the radius of the shock as a function of time on the x-axis. Now, all of the models grow initially until the shock reaches around 150 kilometers, and then it gets stuck right around there. For context, this is shorter than the distance from here to San Diego. These are very small scales of explosions happening on less than a second in time. And then afterwards, some models explode in solid lines, and they presumably will form a neutron star. Others fail, the shock recedes in the dashed lines, and these will likely form a black hole instead. Now, there's no sense, rhyme, or reason into which of these models explode. It's not like the lighter ones explode and the heavier ones fail to do so, or vice versa. It's a bit more complicated. So what we then did was take a step back. If you ever look at a result in 2 dimensions and you don't see a clear trend, you're looking through the wrong lens. And so we took a step back and, without even running a model, just took a look into the inside cores of these core collapse massive stars. And I plot here the density of the inner core. This is a log scale, which means each increase here is a 10-fold increase in density of the innermost core of these massive stars. As you expect, the density drops precipitously as you move away from the innermost core. But the values here go from billions to tens of thousands of grams per cubic centimeter. You have a density, Earth has a density of around 1 gram per cc. These are billions of times denser than normal matter that we encounter every day. I want to draw your attention to this dotted ellipse, where I show an interesting feature for all of these models. You see the red, black, blue, and green lines all drop immediately. They show a sharp cliff dive as the density plummets almost immediately. And these models actually correspond, red, black, blue, green, in the same order to the stars that explode. And if you bring out your onion and you think back to this onion structure of a star, this layer actually corresponds to the region between silicon and oxygen just outside the core. I'll tell you right away that all else being equal, a star that has such a strong silicon-oxygen interface where the density plummets is more likely to explode. And the reason is as follows. Imagine you put on your super suits and you dive into a supernova. In the innermost cores, and the core is collapsing, you see this region of high density. A lot of matter is falling through you. And as it falls through you, it powers a large amount of energy in these magnificent neutrinos. This is right behind you, right behind the stalled shock. And then almost immediately, you see this region where the density just drops. The pressure drops. And the combination of a high energy behind you, behind the shock, and the low pressure ahead of you, ahead of the shock, provides a fertile breeding ground to revive a failed explosion into a successful supernova. Think of the analogy as follows. Now grab your garden hose, turn on the nozzle, and put your thumb on the nozzle. You won't see water pushing out. Now, if you lift your thumb, equivalent to lifting the pressure at this interface, you'll see the water explode outward. No more, no less. And so we decided then to test this hypothesis to see if it's at all accurate, and we designed a machine learning approach. So we used sort of AI, artificial intelligence, to see if this is indeed accurate. And we ran thousands of models through this network, training a computer to predict explosion outcome without running a simulation. And we found that we had around 90% accuracy. Now, this is good because it's no laughing matter. It provides us with some confidence that we're on the right track. But as importantly, every year we use tens of millions of computers, CPUs and GPUs, running for hours to be able to model these explosions. It is extraordinarily expensive in computational time and resources and money. We have grants for that, fortunately. Now, what this shows us is we can predict outcome with good accuracy at a fraction of the computational cost. If you wanted to run a model yourself, you could go and rent from the cloud services like Amazon Web Services, and it would cost you to rent one computer, one CPU, for 1 hour, it would cost you 3 cents. We use hundreds of millions of CPUs for hours. So this is really hiding a savings of millions of dollars. What's next? So moving on to our second ingredient in our MacGyver tool belt, we're going to need a game of billiards. I want to communicate to you that neutrinos interacting with atoms is much like a game of billiards with the balls colliding into each other. And the details on how we can accurately model these collisions, how effectively can a neutrino give all of its energy to an atom inside the shock and hence blow the star up, can make a crucial difference in the final fate of a massive star. And so now I'll show you the same plot you saw on the prior slide, you're not familiar with, shock radius versus time. A runaway shock means explosion. This stalled failure means no explosion. This black line has our all the bells and whistles in this neutrino and nuclear physics calculation. If we then make approximations in how we model these collisions, solve it more coarsely, now the star doesn't explode. If you make even more approximations, the shock recedes even further in. And so the details in how you model the neutrino and nuclear physics in the cores of core collapse supernovae can first prompt the shock further out and ultimately result in an explosion. And the last thing any MacGyver needs is a big computer. This is one such computer we use. It's called Frontera. It's built in Texas. It's funded by the NSF, the National Science Foundation. And you can see that each of these facilities has multiple aisles, and each aisle has multiple cabinets, and each cabinet has multiple drawers, and each drawer has multiple CPUs and GPUs. This requires the equivalent energy of a small town to power. And so if you put together these three advances, these three tools, an improvement in the onion structure and this idea of the silicon-oxygen interface, an improvement in the nuclear and neutrino physics of these billiard ball interactions, and finally the resources on these computers to test and explore our models, we see that in the last decade, we have shattered the paradigm where for over half a century, models have collectively failed to explode to now, where we can not only produce explosions, but produce robust explosions, which begin to agree with observations. So I can now more confidently show you a movie of a 17 solar mass star. You saw in the very beginning. There's the core in the center. You can see the shock forming almost a ghastly presence in the beginning. It forms these small-scale plumes as neutrino heating begins to drive the explosion. Now grows. This is all on a wingspan of around a few thousand kilometers. You can see it's continuing to grow on a timescale of less than half a second. Matter is falling in. The shock is exploding outwards. And we call this a wasp's waist morphology, where you have a large abdomen, a thin waist, and a small thorax. So much matter falls in this explosion that the core actually begins to spin up. And so we can make cores of stars, neutron stars, which can spin as fast as 1,000 times per second. This is now the same model at a different time snapshots. Now a different one, this is 11 times the mass of our sun, not as heavy, 25 and 15 times. All of these explode with different geometries, different structures, but they all do explode. And in fact, we can do more than just say stars explode. In the year 2021, in a Nature paper we submitted, we showed that the energies of these models that we run are generally in good agreement with the energies of stars we actually observe. And I plot on the y-axis here the explosion energy, and on the x-axis the mass of the star. The energy is in betas, named after Hans Bethe from a few slides back. He did some important work on neutrino physics in this context. Now for context, additional, 1 beta is equal to 10 to the 51 ergs, an FOE. An erg is the amount of energy it takes for an ant to do a push-up in Earth's gravity. So imagine all of these ants hard at work. In the black dots, we showed the models from our own calculations, and the colored points are observations from instruments like the Hubble Space Telescope. And while not perfect, we see they're able to reproduce the general trend of energy quite well. This was an important step forward. What more can we say? You may know about gravitational waves, which are ripples in space and time that are powered by 3 things. First, you need something big, something asymmetric, and something fast. And allow me to remind you that supernovae are all 3. And so when a star explodes, some matter goes out, some matter falls in, and this can excite earthquakes, not dissimilar from the one we experienced earlier this morning, but on the surface of a neutron star. This is a star quake, and these earthquakes in stellar environments can excite gravitational waves. And we can see those with instruments like LIGO, the Laser Interferometry Gravitational Wave Observatory. But we can also build instruments on the moon. This is an idea I was involved in producing what's called a lunar gravitational wave antenna. Because it turns out there are fewer people and less traffic on the moon. And so there's less noise, background pollution, when you're trying to see very faint, distant explosions and their gravitational waves. And in fact, we can actually hear these sounds. They lie in the kilohertz frequency range, which means they're audible to us and they're audible to your pets. Here's what the sound of 2 black holes, not a supernova, merging sounds like as detected by LIGO. Now that burp is followed by a rumble of an actual model that we developed of an exploding star. This is what that sounds like. Now what if the core is rotating? In that case, you can hear a distinct pattern of rotation if you listen carefully in the first second. You hear a chirp. Now I want to qualify what I said with the following. If you do actually hear a supernova in real life, you have much more pressing concerns to worry about. We can also see neutrinos because they're produced in copious abundance from these explosions. I'll show here one such detector. This is a prototype of DUNE. DUNE is the Deep Underground Neutrino Experiment. And it's essentially a steel cage. It's not gold. That's just reflective coating and the light source in the center. And when this is built up to full scale, it will be part of a 1,000-kilometer underground tunnel from South Dakota to Illinois, culminating in a 40-kiloton pool of liquid argon. Argon is sensitive to neutrinos. And with instruments like this and the whole global network of these instruments, we can do so much more. In 1987, when we saw the first nearby supernova, we gathered only around 24 neutrinos, depending on whom you trust. For a next-gen event, we should be able to see millions of these neutrinos. And they're important because neutrinos and gravitational waves provide insight into the first seconds of explosion all the way down to the innermost core, which is otherwise hidden from us. When we see light from an explosion, it's not at seconds, it's at days, months, in the case of Cas A, centuries and millennia. And they show us not the core of the star, but the outermost layers. And so the core, the engine, And essentially, the theories to refute or verify our understanding remain hidden unless we see neutrinos or gravitational waves. But these are exceedingly rare, a few per century in the Milky Way. So where do you go from here? I'd like to introduce to you my idea of this trickle-down economics. These simulations are so expensive, we only have a few to date. Even fewer have the correct neutrino billiard ball physics. Fewer still are carried out to late times with templates in neutrinos and gravitational waves in light to compare directly with observations. And to really drive that point home, I show here the number of supernova detections in the last decades. This is a log scale. Each increase here corresponds to a 10-fold increase in the number of supernovae detected. Now, out until 2010, we had around 800 supernovae observed. Many were at Carnegie through the Magellan telescopes and through the Carnegie Supernova project, and also through the Hubble Space Telescope. Out to 2020, we had around tens of thousands of detections, a sharp increase. There are instruments like ZTF, Assassin, Atlas, STSS. These abbreviations should mean nothing to you. What matters is that in the next decade, with the launch, or with the opening of Rubin LSST, the Large Synoptic Survey Telescope, we expect to see not tens, not thousands, but millions of supernovae detections. This is not an exponential growth, this is a super exponential growth in the next 10 years. But if only 5 years ago we cannot even blow up a star, where do we lie in theory? Are we ready for this advent? Now I'm going to shift the Y scale down here to 1, because in 2017, I produced one of the first explosions of a star, which you've now seen, a 17 solar mass star. Out to 2023, we had around 100 models. This is so much fewer the number of observations we have that it even makes the observation increase, while still significant, seem less profound. And so where do we go from here? How do we couple the first milliseconds of explosion out to the centuries of observations? How do we go from the inner depths of these massive stars, from their cores, out to the parsecs of these beautiful explosions, all at vastly differing scales, with vastly differing physics? Well, I'm glad you asked, because with some colleagues, we turned this pipe dream into a pipeline. This is the essential framework here, but what's really important is we're able to take on this daunting challenge. It's difficult to model a star for a second, let alone for a day, that's 86,400 seconds, or a month, that's 2.5 million seconds, let alone a year, that's pi times 10 to the 7, a millennia, billions of seconds. And so with my colleagues, we decided that yes, we would still be daunted, but we would try to do this anyway. And so we connected and ran the simulation in entirety, from seconds to days to months and eventually to centuries. And we couple, essentially, the theory. This is what we produced in the core collapse of a neutrino-driven explosion in the first second to observation. This is Cas A at around 400 years. I want to come to a not quite a near conclusion here. Recall in the very first slides where I asked you to remember this three-lobed structure of Cassiope A. We have these three distinct plumes, these three distinct features in iron. In one of our recent models, here's what we get. We're able to reproduce those same three distinct structures in iron. This is where the iron inner blood cells come from. Not the screen, but the star. And this is one more nail in the coffin that the theory of neutrino-heated supernovae is correct. We're able to produce not just explosions, but explosions with the right energies, with the right elements, with the right structures. And we're just getting started. Unfortunately, I cannot do the same for my talk, as I'd like to come to a proper near conclusion here. It advances in stellar physics, this silicon-oxygen interface in the onion structure of a star. It advances in the details of neutrino and nuclear matter interactions, the billiard balls metaphor, together with the advent of proper supercomputers to run, test, explore these models, have conspired with the upcoming promise of observational bounty through instruments like the James Webb Space Telescope, like Rubin LSST, to provide a unique window in time, a unique opportunity to more resolutely, more confidently advance and address the long-standing supernova problem. We are poised on this precipice, on the verge of exciting discovery. You may be familiar with Maslow's hierarchy of needs, which says that to reach self-fulfillment, you must first have your physiological needs, food, water, shelter, then our psychological needs met. I come to humbly, modestly, with a bit of tongue-in-cheek, propose the Vartanyan hierarchy of supernova theory. For decades, we have been on this bottom rung, just trying to get stars to explode. And this, I want to emphasize, has been built on a communal effort of collaboration spanning decades between theorists and observers, between Romeo and Juliet. And now, advances in this front in the last 10 years have allowed us to climb up this bottom rung and produce stars that explode with the right energies, with the right signatures, with the right elements, with the right structures, and eventually want to converge to an answer as to where do neutron stars come from, where do black holes come from, where do our atoms, where do we come from, what is the final fate of massive stars. Liberated by these advances in the last decade, we can now begin to ascend this narrative arc, and in so doing, forge a more intimate connection between the theory of today and the observations of tomorrow. Thank you.
Again, I remind people, if you have a question, if you can come to the mics, because so the online folks can, if we get a little light, I can't see. A second. All right, you start over here.
So what happens to stars that are too small for supernovas?
Great question. And what happens to stars that are too small to go supernovae? Our sun is one of those stars. When you don't have enough mass to reach this critical threshold for explosion, you're not going to explode. So our star, our sun, will not explode. It will likely puff out. And whether it reaches Earth's radius as it expands, whether we're engulfed is an open question, but after it puffs out, it will then shrink and leave behind a tiny compact object. It will not explode.
You mentioned the phenomena of the shock wave stalling. Why does the shock wave stall in a vacuum?
Yes, it's good. So the shock wave is not forming or being launched in a vacuum. It's forming inside the depths of a massive star at very high densities, where the pressure of all of the matter ahead of it stymies it and prevents it from exploding.
Did you guys use the simulations, the supernova simulations, or the images of nebulas and trace them back to get the sounds of supernovas?
If I heard it correctly, you asked if we use supernova simulations to make those images, and where do we get the sounds?
Did you use the simulations to get the sounds?
Yes. So the simulations, the sounds I showed you were from the first seconds of explosion, from the gravitational waves produced there. We don't have sound throughout the rest of the simulation, but that's not hard to do. That's actually a very good idea. It'd be good to have the acoustics of an entire explosion out to days. Thank you.
Thank you for the amazing talk, and thank you for mentioning Victor Hapatsumian's importance to astrophysics. My question is, the study of high-mass protostars is also quite important to the Vartanyan hierarchy of ascent theory. I was wondering how the ever-growing community in high-mass protostar theory can help the hierarchy.
I apologize. Can you please repeat the last bit and cut out for me?
How can the study of high-mass protostars, as it's still in its early stages, help the supernovae theory?
Okay, so essentially, what about planets in supernova theory? Is that right?
High-mass protostars, sorry.
Oh, high-mass protostars. I apologize. Yes. Okay, excellent. So before a star is born, it's a protostar. It's a baby star. And these high-mass, in some cases, we found extremely high-mass stars dating back to the first blinks of our universe right after the Big Bang. And what's important about massive protostars, which may then later collapse and form stars, is that this is where the cradle of a stellar birth happens. And if you go back to the first moments of the Big Bang of our early cosmic universe, this is where the first elements were made. So elements like hydrogen and helium, the air around this was largely made in the Big Bang explosion. Now from then on, massive stars took these elements and made heavier and heavier elements, carbon, oxygen, all the way up to iron. More immediately, massive protostars provide the environments, and in this talk, for the sake of clarity, for time, and for my sanity, I neglected a lot. I only consider the star itself, but what about its environment? And protostellar environments can shape the area around the star when it explodes. You saw the image of Cassiopeia A with the light echo off the dust? That becomes even more prominent when we consider that it's not just the birth of a star that matters, but its environment. It's really nature or nurture. And so in that case, protostars provide the nurture to the star's own inherent genetic nature. Thank you.
If I heard you correctly at the beginning of your talk, you said we don't observe that many supernovas in a century. And so what you just touched on, environment and the makeup of the star, I guess, help determine if it occurs or not. So if you don't reach a certain mass, it's not an absolute thing that you're going to have a supernova. And also, I was wondering if Isaac Newton inspired your haircut.
Thank you for the comment on my hair. I've been waiting all day for that comment. Yeah, so the question is really, there's a lot of uncertainty in this environment if the star's massive enough to explode. Let me remind me if I miss a part of the question. And so I want to say that so much of this is yet unknown. In many cases, we, as a community of people who blow up stars, are limited by the structures of these stars themselves, these initial conditions. And even though we only see a few per century, we only see a few per century in our Milky Way, but our telescopes can detect way beyond that. That's how we see tens of thousands to millions. And so hopefully with a growing body of calculations, of observations that go hand in hand, we're not out here collecting stamps or collecting coins. We're not numismatists, we're not philatelists. We're doing science here. And with a growing body of observations and simulations, we can then begin to constrain for this huge parameter space. What's the role of the detailed physics? What's the role of the environment? And what's the role of their sensitive interplay? Very good question.
Oh, hi. Thank you so much for everything. I learned so much today. So I have a question about the supercomputers. So you were saying that they use like energy from a whole town or something like that, right? Would you be using anything like how Microsoft is doing with qubits or something like that soon? And if you would, what plans do you have with that?
Yes. Again, please chime in if I skip over a part of your question, but the computers we use, not as you would imagine, they're not a monitor with a brain, they're just the brain. That's why we don't think, we use their brains there. And so the operating system there is not a Windows, it's Unix. Windows does have tools like visuals that may be useful in post-processing the data and analyzing the data. But to run a simulation, you need a very distinct computer environment that these networks provide, and even then it's still a difficulty. And so we can use environments, if you're familiar with codes like C, C++, GNU, and environments that can support those codes to solve those equations in a star. Does that address your question?
I think so. Maybe.
Oh, quantum computers, yes, I'm sorry, yes. I missed the quantum. Okay. So quantum computers are fascinating because they're really a race against error. You want to limit how much error you can have in a simulation, in any calculation that's introduced when you use quantum bits or qubits. Now, 3 years ago, there was a big breakthrough, and there are more every day, where a quantum computer was able to solve for matrix inversion. And that is not just an artifact of linear algebra, that's a very real presence in these calculations. We have a lot of big databases that are multiplied and divided by each other. And so we use a lot of algebra involving multidimensional matrices. And were a qubit or a quantum computer to manifest and fulfill its potential, we could see large accelerations in these calculations. But I don't see that as an immediate future. That's something that's larger on the horizon.
Great presentation, sir. The two sentences that I understood. Quick question. So in terms of you said there are only a handful of neutrinos that were harnessed. Down the line, if they harness more, what could be the potential application for that were harnessed?
Right. Can we solve the energy problem through neutrinos? Unfortunately not. It requires 40 kilotons of one chemical, liquid argon, to see a few thousand neutrinos. And we source it indirectly, not directly. There are prospects underway to use the entire Mediterranean as one big water pool to detect neutrinos. And even then, we can maybe see millions. Each of these has a comparably small energy, so if you're able to collect all of their energy, you would have maybe enough to pay for one light bulb in that building. So I am being a little bit loose here, but they're just such small, weak interactions that it's unlikely in the near future. Thank you.
I'll just remind everybody our last lecture for the series is May 6th. That's a Tuesday. We didn't want to do it on Cinco de Mayo, so you can go have Cinco de Mayo and then still come out for a lecture. And that's Tony Pirro, who many of you have heard before, great speaker again. So we'll end our series with Tony, and those will become available tomorrow, right? So make sure 10 a.m. tomorrow. Thank you, Natasha. So hope to see you all then, May 6th. Thanks. Thanks, David, again. It's really great. But never know what your job is.